The grass is green in color, right? In reality, grass isn't green. Your eyes have 3 color receptors, therefore, it's only green to you. Since a dog only has 2, grass is yellowish to them. So, what exactly is the color of grass? It's not beige because it's not green. Until you see it, it simply is. What about the rest of the world, if color is only a perception? Consider the earth beneath your feet. It is solid, but if you zoom in deep into the atoms that make up the floor, it's mostly empty space. So why don't we just collapse through the earth? Because what you're feeling isn't physical. As your body weight touches the floor, atoms are forced against one another. Their electrical fields then repel, creating what is known as the force. You're merely energy interacting with energy, not actually touching the floor. To put it another way, everything you experience is merely electrical signals in your brain. The screen you're looking at, the sound in the video, and even your bodily sensations are all simply energy being interpreted by your brain. Our brain has only ever processed electrical messages. It has never seen light or touched anything. Therefore, reality is really a high-resolution illusion that your mind created. And if everything you've ever seen, felt, or thought was really a mental simulation produced by your brain interpreting energy. So, are you dreaming with your eyes open, or are you truly awake? You're standing in the middle of a large field, and you and a friend each hold one end of a long rope. You both stand far apart, pulling gently, and you can feel the tension through the rope. Every move your friend makes, whether pulling or releasing, affects you immediately because you're connected. The rope serves as a clear link between both of you. Everything that happens at one end of the rope will influence the other. This is how we usually think the world works. Things affect each other in clear, predictable ways. If you push something, it moves. If you pull a rope, the other end moves too. Simple, right? Everything happens because of what's around it, connected by physical forces we can see and understand. This idea is called locality, the belief that things only influence each other through direct contact or a clear chain of events. But now, imagine something strange. You and your friend throw away the rope, so there's nothing connecting you. Yet, when you pretend to tug on your end, your friend feels it instantly. No delay, no string between you. Your friend could be across the field, or even miles away, but somehow the pull still reaches them. It doesn't make sense, and yet this is exactly how nature works at the tiniest levels. At smallest level, particles can be connected across vast distances without anything visible linking them. It's as if reality itself is woven together by something unseen, something deeper than space and time. No, this isn't like your phone sending a message wirelessly. Your phone relies on signals, waves that travel through the air, bouncing between towers and satellites at the speed of light. Those signals can be detected, measured, and traced. But what scientists have found is far stranger. When they take a single atom, split it, and send its halves to opposite ends of the Earth, something impossible happens. When they change one half, the other reacts instantly. No signal, no delay, no physical link of any kind. It's as if reality itself is woven together by something unseen, something deeper than space and time. But what could that be? If nothing connects them, yet they move as one. Does that mean separation is just an illusion? And if the universe behaves this way at its core, then what does that say about the world we live in? Is everything we see, everything we call real, just a shadow of something deeper? Maybe separation is just an illusion. That all matter and energy, the universe, the stars, and you are linked in ways that transcend space and time, in ways we can't yet fully understand. What if the world around you is a carefully constructed illusion, a shadow of something far stranger and far deeper? If separation is an illusion, what is it that connects everything? Could the entire universe be part of a hologram, where everything we experience is just a projection? Or could it be a multiverse, where infinite realities exist and the boundaries between them blur, leaving us to feel separated when, in truth, we are part of a much larger whole? Or maybe we're living inside a simulation, a creation of advanced beings, with our reality nothing more than lines of code. What is the universe really? Could it be that the universe as you know it does not exist? The problem starts with a paper. In 1935, Albert Einstein sat down with his colleagues Boris Podolsky and Nathan Rosen. Together, they drafted what would come to be one of the most unsettling papers in the history of physics. The trio, driven by a shared frustration with the chaotic dice-rolling nature of quantum mechanics, intended to set things straight. They titled their work, "Can Quantum Mechanical Description of Physical Reality be Considered Complete?" A question that would reverberate far beyond the ivory towers of academia. Einstein, the elder statesman of physics, had long been troubled by the direction quantum mechanics was heading. To him, the universe was a grand clockwork machine, its gears and cogs ticking away with precise predictability. Every effect had a cause, every action a reaction. This was the world he cherished, orderly, local, and grounded in common sense. But quantum mechanics, it suggested that particles could exist in two places at once, that they could seemingly decide their fate only when observed. It was a universe built on probabilities, not certainties. A world that rolled dice behind the scenes, and Einstein hated it. For centuries, the universe seemed an unbroken system of cause and effect, its workings captured by Newton's equations and guided by the belief that reality existed independently of the observer. This classical view, known as local realism, gave humanity a firm foundation for understanding the cosmos. It was simple, clear, and reassuring. Local simply means that nothing in the universe can travel faster than the speed of electromagnetic waves, for example, light. And thereby, no matter or force or information can be transmitted from one point in space to another faster than this speed. This is derived from the special theory of relativity. For instance, if NASA wants to increase the speed of the Mars rover by pressing the accelerate button here on Earth, it will take at least 3 minutes for the electromagnetic wave signal to reach the rover and for it to accelerate. There is no breaching this law anywhere in the universe. On the other hand, the concept of real is quite intuitive. In the case of any macroscopic object like a football, a planet or a star would be considered real because they exist at a specific location in space at a specific point in time with a specific momentum, energy. In classical physics, location in space and time, momentum, energy are considered to be deterministic and objective properties of an object, regardless of whether the object is being observed by someone or not. Hence, they were considered real. It claimed that objects possess properties whether or not anyone observes them. A rock is solid, heavy, and grey, regardless of whether it's held in your hand or left alone on a mountainside. The moon, as Einstein famously quipped, is still there even if no one looks at it. This belief in an objective, observer-independent reality was as natural as breathing. Together, these ideas formed a sturdy framework for understanding the world. They aligned with the mechanics of Newton and Maxwell, painting a picture of a predictable, local universe that behaved like a well-oiled machine. From the movement of planets to the trajectory of a cannonball, the cosmos appeared governed by laws that were timeless, universal, and transparent. Then, everything changed. In the early 20th century, as scientists began peering into the very fabric of the universe, they stumbled upon something truly baffling. They discovered that at the atomic scale, particles didn't behave in the way we intuitively expected. Classical physics had led us to believe that everything in the universe followed a set of predictable, straightforward rules. Matter seemed like a collection of tiny marbles, billiard balls moving along clearly defined paths. But when scientists looked closer, especially at the microscopic level, they found something entirely different. Atoms and subatomic particles didn't behave like the objects in the everyday world. Instead, they exhibited strange, seemingly unpredictable behavior. And what was even stranger was that this behavior didn't follow the comforting logic of local realism. The idea that objects only interact with their immediate surroundings and that everything has a definite state, independent of observation. This was when the world of quantum physics began to reveal itself. One of the most famous experiments that highlighted this bizarre behavior was the double-slit experiment, first conducted by Thomas Young in the early 1800s. In the context of modern physics, the experiment was revisited by physicists in the 20th century with particles like electrons. The setup was simple, but mind-boggling. Imagine two slits with a screen behind them. As particles, represented by small dots, approach the slits, they are directed toward either slit A or slit B. If there is no observer, the dots, representing particles, behave like waves, spreading out and passing through both slits, forming an interference pattern on the screen. However, when an observer is introduced, shown by a person standing beside the slits, the dots immediately behave as solid particles and forming a pattern consistent with what you'd expect from solid objects. The more you watch, the more the particles behave like little marbles, not like waves. The shift from wave-like behavior to particle-like behavior is as if the act of watching determines the reality of the particle. This experiment left scientists scratching their heads. The outcome seemed to depend on whether or not an observer was watching the experiment. It wasn't just that the particles acted strangely, it was the mere act of observing the particles somehow influenced their behavior, causing them to act like either a wave or a particle depending on how they were measured. Imagine that you could flip a coin. If no one is watching, the coin might land on both heads and tails at the same time, creating an uncertainty in the outcome. but the moment you look at the coin, it settles on either heads or tails. It's like the coin doesn't decide on one side until you actually observe it. How could the mere act of watching determine the path a particle took? This discovery hinted that reality might not be as independent as we thought. Particles didn't seem to have definite properties, like position or momentum, until measured. This defied the realist notion that objects exist in a specific state regardless of observation. Instead, it suggested a probabilistic universe, one in which outcomes were determined only when interacted with. It was as if the particles were playing coy, refusing to show their hand until they absolutely had to. Then came the phenomenon of entanglement, first theorized by quantum mechanics and later tested experimentally. When two particles interact and become entangled, their properties become linked. Measure the state of one particle and you instantly know the state of the other, no matter how far apart they are. This seemed to violate the principle of locality. How could a particle know what had happened to its distant partner faster than any signal could travel through space? It was as if the particles shared a secret connection, one that operated outside the bounds of classical physics. Einstein, for all his genius, struggled to accept this. He famously derided it as spooky action at a distance, a phrase that captured both his skepticism and his unease. To him, this apparent violation of locality was a sign that quantum mechanics was incomplete. There had to be some hidden variables, some deeper mechanism that preserved the principles of local realism. Without them, the universe, as he understood it, predictable, rational, and orderly, would collapse into chaos. But quantum mechanics kept producing results that defied classical intuition. Werner Heisenberg's uncertainty principle showed that certain pairs of properties, like position and momentum, couldn't both be known precisely at the same time. The more you knew about one, the less you could know about the other. This wasn't a limitation of our measurement tools, it was a fundamental feature of nature. It hinted that the universe wasn't a clockwork machine, but something far more dynamic, far less deterministic. By the 1930s, the growing body of evidence against local realism reached a breaking point. Einstein, Podolsky, and Rosen published an important paper in which they claimed that the whole formalism of quantum mechanics, together with what they called a reality criterion, imply that quantum mechanics cannot be complete. The EPR peer had enough of what they think as a nonsense of quantum mechanics and write the famous EPR paper as an attack. In it, they proposed a thought experiment. Imagine, they suggested, a pair of particles that interact and then fly apart in opposite directions. According to the theory of quantum mechanics, these particles remain entangled, their states mysteriously linked, no matter how far apart they are. Measure one, and you instantly know something about the other. But this seemed impossible, or at least it should have been. For one particle to know what happened to the other faster than the speed of light would violate the principle of locality, a cornerstone of classical physics. Locality states that objects can only be influenced by their immediate surroundings, not by distant events. To Einstein, this spooky action at a distance was an affront to the very fabric of reality. They argued that the only way to make sense of this was to assume that the particles had hidden variables, some underlying properties that determined their states all along. In other words, the particles weren't deciding their fate at the moment of measurement. They had definite properties the entire time, If these hidden variables existed, then quantum mechanics was incomplete, just an approximation of a deeper, more predictable reality. But not everyone saw it Einstein's way. Niels Bohr, one of the architects of quantum mechanics, pushed back with equal vigor. Bohr argued that the EPR paper misunderstood the nature of quantum reality. To Bohr, the universe didn't operate like a clock or a dice roll. It was something stranger, something deeply tied to the act of observation. Reality, he claimed, wasn't something out there, independent of us. Instead, it was something that came into being only when measured, when observed. When Einstein say that, God doesn't play dice, Bohr replied and says, Einstein, stop telling God what to do. The clash persists for decades, and the answer didn't come until the 1960s, when physicist John Bell entered the field. Working as a quiet, methodical physicist at CERN in Geneva, John Stuart Bell's primary focus was the complex mathematics underlying particle accelerators. His work was meticulous, rooted in practicality, and far removed from the philosophical debates raging over quantum mechanics. But in the quiet hours, Bell found himself returning to an old problem, one that had haunted physics for decades. It began with a paper he stumbled upon, a work by David Bohm that rekindled the fire of Einstein's challenge to the strange, probabilistic world of quantum theory. Most people in the scientific community dismissed Einstein's resistance to the quantum field, insisting quantum mechanics was indeed weird but workable. David Bohm, however, took Einstein's skepticism seriously. He proposed an alternative theory, one involving hidden variables, parameters beneath the quantum surface that might restore determinism. To mainstream physicists, Bohm's theory seemed untestable, more philosophy than physics. But to Bell, Bohm's work planted a seed. What if there was a way to test whether the universe followed Einstein's classical rules, or whether quantum mechanics' strange predictions were in fact real? Bell spent months poring over the equations. His insight was revolutionary. He realized that the question of locality, the idea that an object can only be influenced by its immediate surroundings, could be tested mathematically. He developed what we now call Bell's theorem, a framework that allowed physicists to pit Einstein's classical worldview against the bizarre implications of quantum entanglement. The crux of Bell's theorem lay in something called Bell inequalities, mathematical expressions that made specific predictions for experiments involving entangled particles. If the universe was local and governed by hidden variables, then measurements on entangled particles would obey these inequalities. If not, if the universe was as strange as quantum mechanics suggested, then the inequalities would be violated. Bell had transformed a philosophical debate into an empirical question, one that could be settled through experiment. To understand the implications of Bell's theorem, imagine a pair of twins separated at birth and sent to opposite sides of the world. Despite their distance, every time you ask them the same question, say, "What's your favorite color?" they respond with the exact same answer, instantly and without hesitation. Now imagine you vary the question, asking them about their favorite animal, their favorite number, and so on. No matter how random or varied the questions, their answers always match perfectly and appear instantaneously. It's as if the twins are communicating faster than the speed of light, or even stranger, as if their responses were somehow predetermined by some hidden factor. Bell's theorem essentially asked, Are the twins secretly exchanging information faster than light? Or is there something deeper going on? His work revealed that no hidden variable theory, operating within the constraints of locality, could explain the results predicted by quantum mechanics. If entangled particles behaved as quantum theory suggested, then the universe wasn't local. It meant that actions performed on one particle could influence another particle instantly, no matter how far apart they were, without any signal passing between them, unconstrained even by the speed of light. Yet for all its power, Bell's work initially languished. In the 1960s, the technology needed to test his theorem simply didn't exist. His ideas were brilliant, but they were ahead of their time. For years, they remained largely theoretical, discussed in small circles of physicists, but largely ignored by the broader scientific community. But, as it was always happened in science, when a scientist hit a dead end, another one opened the new door. John Clauser was a young graduate student at Columbia University when he stumbled upon a paper that would forever change the trajectory of his career. It wasn't a widely celebrated work at the time. In fact, it was largely overlooked. But to Clauser, the paper by John Bell, published in 1964, was different. It challenged one of the most deeply held beliefs in physics: the idea that the universe was governed by local realism. Bell's theorem suggested something far stranger. Bell proposed that entangled particles, those strange quantum pairs whose states are inexplicably linked, could exhibit correlations that defied any explanation rooted in classical physics. For Clauser, the implications were staggering. The universe might not work the way Einstein imagined it, and if Bell was right, the boundaries of locality were not boundaries at all. But Bell's work was theoretical. It proposed a way to test the hidden variables Einstein believed in, but no one had yet attempted such an experiment. Clauser, brimming with curiosity, wrote a letter to Bell. He wanted to learn more, to understand the depths of this bold idea, and perhaps to take it further. Bell, ever the gentleman physicist, replied. Their correspondence planted a seed in Clauser, a determination to test this theory not just on paper, but in the real world. 3 years after their first correspondency, the seed's potential finally really ready to be realized. Clauser set up an experiment that would challenge one of the deepest assumptions about reality: the principle of locality. If quantum mechanics was correct, then entangled particles could be connected across vast distances in ways that defied classical physics. But if Einstein's intuition was correct, some hidden variables would be responsible for the apparent connection. The setup was based on Bell's theorem, which provided a mathematical way to distinguish between the predictions of quantum mechanics and any theory that relied on local hidden variables. Now, before we proceed further, let's first understand what is polarization. Light is a type of electromagnetic wave, which means it has electric and magnetic fields that vibrate as the wave travels. Normally, light waves vibrate in many different directions. Polarization is like putting sunglasses on these waves by using polarizing filters, making them vibrate in just one direction. These filters block certain directions of light waves and let others pass through. Now, let's get back to our topic. Clauser and Friedman designed an apparatus to measure the polarization of entangled photons particles of light. The experiment involved producing pairs of entangled photons from a calcium atomic cascade. When a calcium atom is excited to a higher energy state and then decays, it emits two photons that are entangled in their polarization states. These photons were then sent in opposite directions to two separate detectors placed several meters apart, ensuring that no information could travel between them at the speed of light within the time of measurement. The key to the experiment was how the polarizations were measured. Each detector contained a polarizer, which could be rotated to different angles. According to quantum mechanics, the outcome of measuring one photon's polarization would be correlated with the outcome of the other, even though the measurement choices were made independently. In simple terms, it means that if one photon has a spin up, then the other will have a spin down. This means they are both quantum entangled, which means we get one vertically polarized photon and the other horizontally polarized photon. Now, if we could find out the spin of one photon, we will get to know the spin of other photon also. If local realism were true, then these correlations would follow Bell's inequality. If quantum mechanics were true, they would exceed it. Clauser and Friedman measured the polarization correlations of entangled photons at different angles and calculated a value known as the CHSH parameter, a refined form of Bell's inequality developed by Clauser, Horn, Shimoni, and Holt. Classical physics predicted that this value could never exceed 2. However, quantum mechanics predicted a maximum violation of approximately 2.82. When the experiment was conducted, Clauser and Friedman found a violation of Bell's inequality. The measured correlations between the photons exceeded the classical limit, aligning with quantum mechanics predictions. This result strongly suggested that no local hidden variable theory could explain entanglement. The photons were indeed connected in a way that defied locality, meaning that their states were determined instantly, regardless of distance. While groundbreaking, Clauser's experiment had certain limitations. One major issue was the locality loophole. In their experiment, the two detectors were placed far apart, but not far enough to completely rule out the possibility of some kind of hidden communication between them. To truly test Bell's theorem, future experiments would need to ensure that the detectors were so far apart that any such communication would be impossible, even at the speed of light. It was Alain Aspect who took the baton and pushed the boundaries of experimental physics to close this critical loophole. By the late 1970s and early 1980s, Aspect, a French physicist with a sharp mind and a relentless curiosity, set out to refine and expand on the foundational work of Clauser and Friedman. Aspect's mission was ambitious: to design an experiment so precise that it would leave no room for doubt. If hidden variables existed, they would have to reveal themselves under his watch. At the time, Aspect was working at the Institut d'Optique in Orsay, France, under the guidance of a leading physicist, Jean Dalibard. His goal was clear: create an experiment that not only tested Bell's inequalities, but also did so in a way that ensured the two detectors were completely independent of each other. To do this, Aspect introduced a groundbreaking innovation: a method for switching the settings of the detectors during the experiment, while the entangled photons were already in flight. This random switching mechanism was the key to addressing the locality loophole. The basic structure of Aspect's experiment built upon Clauser's earlier design, but with several crucial upgrades. He used a process called spontaneous parametric down conversion, SPDC, to create pairs of entangled photons. These photons, once generated, traveled in opposite directions to two separate detectors located far apart. The challenge was to ensure that the settings of each detector were determined only after the photons were already on their way. This would prevent any possibility of the photons knowing the detector settings in advance. One of the key criticisms that skeptics of earlier experiments had raised. To accomplish this, Aspect and his team developed an ingenious system using high-speed electronic devices to randomly switch the polarization settings of the detectors during the experiment. These devices operated so quickly that the choice of detector settings happened within a time frame shorter than it would take for light to travel between the two detectors. In other words, even if some hidden mechanism were trying to coordinate the behavior of the photons, it wouldn't have enough time to transmit information between the detectors. This was a crucial step in ensuring that the experiment adhered to the principle of locality. Aspect's setup required painstaking precision. The detectors needed to be perfectly aligned, and the timing of the switching mechanism had to be calibrated down to nanoseconds. It was a feat of experimental engineering that pushed the limits of what was possible at the time. The lab in Orsay became a hub of activity, with Aspect and his colleagues working tirelessly to fine-tune every aspect of the apparatus. When the experiment was finally conducted in 1981, the results were nothing short of remarkable. The correlations between the entangled photons measurements once again violated Bell's inequalities, confirming the predictions of quantum mechanics and ruling out the possibility of local hidden variables. Aspect's work provided even stronger evidence that entangled particles were connected in a way that defied classical explanations. It was as if the two photons were communicating instantaneously, regardless of the distance between them. But Aspect didn't stop there. Over the next 2 years, he conducted a series of additional experiments to further solidify his findings. One of these involved changing the experimental setup to test different configurations of the detectors and polarization settings. In every case, the results were consistent with the predictions of quantum mechanics. The violations of Bell's inequalities held firm, leaving little room for doubt. Despite the success of Aspect's experiments, they were not without their own challenges and limitations. For example, while the random switching mechanism was a significant improvement, it still relied on a pre-programmed electronic system to determine the detector settings. This left open a small possibility, however unlikely, that some hidden factor could influence the system. Additionally, the detectors, while more advanced than those used in Claus's experiment, still weren't perfect. Nonetheless, Aspect's work represented a monumental leap forward. It was the first experiment to address the locality loophole in a rigorous and systematic way, and it set the stage for even more precise tests in the years to come. This time, Anton Zeilinger entered the scene. Based at the University of Vienna, Zeilinger had already built a reputation as a brilliant experimentalist with a knack for tackling quantum mechanics' most puzzling challenges. In the 1990s, he embarked on a mission to refine and expand upon the work of Bell, Claus, and Aspect by addressing not only the locality loophole, but also other critical gaps like the detection and freedom of choice loopholes. The detection loophole arose from imperfections in the experimental setups. The freedom of choice loophole questioned whether the choice of measurement settings could somehow be influenced by hidden factors, introducing bias. Zeilinger's experiments sought to systematically eliminate these doubts. One of Zeilinger's early landmark experiments took place in 1998, when his team demonstrated quantum teleportation for the first time. While not directly a Bell test, it showcased the astonishing capabilities of entangled particles, setting the stage for more precise experiments. This experiment used photons as entangled particles and involved transmitting the quantum state of one photon to another over a distance using entanglement. Zeilinger's success with teleportation showed just how well entanglement could be manipulated and controlled, offering a new level of experimental sophistication that would prove crucial in testing Bell's theorem. In 2007, Zeilinger and his colleagues conducted a groundbreaking Bell test experiment on the Canary Islands. The setup was as much an engineering feat as it was a physics experiment. Entangled photons were generated at a central station and sent to two detectors located on separate islands, La Palma and Tenerife, over 144 kilometers apart. This distance far exceeded anything attempted before and ensured that even light traveling at its incredible speed wouldn't have time to relay information between the two detectors before measurements were completed. This was critical for closing the locality loophole. The team faced enormous technical challenges. To send entangled photons across such a vast distance, they relied on an optical free space link, which required precise alignment of telescopes. Atmospheric disturbances posed a significant problem, as the photons could be scattered or lost during transmission. To overcome this, Zeilinger's team developed sophisticated techniques to stabilize the link and maximize the photons' chances of reaching their destination. The results of this experiment were stunning. The entangled photons displayed correlations that once again violated Bell's inequalities, confirming the predictions of quantum mechanics. What made this experiment stand out was its sheer scale and rigor, providing further evidence that locality could not explain the behavior of entangled particles. But Zeilinger wasn't finished. His attention turned to the freedom of choice loophole, a more subtle but equally important concern. To address this, Zeilinger's team devised an ingenious method using distant quasars, celestial objects, billions of light-years away, as sources of randomness for determining the detector settings. In a 2018 experiment, Zeilinger's team created entangled photons and sent them to two detectors. Instead of using a random number generator to determine the measurement settings, they used the light from two quasars to decide how the photons would be measured. Because the quasar's light had been traveling for billions of years, any influence on their random outputs would have to have originated long before the experiment, or even the Earth existed. This made it virtually impossible for hidden variables to influence the settings. The experiment was a triumph, closing the freedom of choice loophole in a way that was as elegant as it was thorough. The results once again aligned with quantum mechanics, reinforcing the idea that entanglement was a fundamental property of the universe, not a byproduct of hidden variables or classical explanations. In 2022, the Nobel Prize in Physics was awarded to John Clauser, Alain Aspect, and Anton Zeilinger for their pioneering experiments with entangled photons, which proved the reality of quantum non-locality. The announcement, made by the Royal Swedish Academy of Sciences, recognized decades of work that had challenged classical views of reality and confirmed that entanglement was not just a theoretical curiosity, but an undeniable physical phenomenon. At the ceremony in Stockholm, the laureates were celebrated for their groundbreaking contributions. Clauser, who had conducted the first experimental test of Bell's theorem, was honored for setting the foundation. Aspect's refinements in the 1980s had closed critical loopholes, and Zeilinger's work had expanded entanglement into new domains, even laying the groundwork for quantum communication. With the world watching, the prize served as a defining moment in physics. It was a recognition that reality, as we perceive it, is deeply shaped by the strangeness of quantum mechanics. As they received their medals, the question loomed larger than ever. If the universe does not obey local realism, what deeper truths remain undiscovered? The confirmation of non-locality changes everything we thought we knew about reality. If particles can influence each other instantly across vast distances, then the universe isn't built on simple, local connections. It means that space itself may not be what we think it is, that everything could be linked by some hidden structure beyond our understanding. This raises strange possibilities. Could reality be more like a web of information rather than a collection of separate objects? If nothing is truly isolated, then what we experience as here and there might be an illusion. This challenges the way we understand cause and effect, time, and even free will. Some scientists think this could mean the universe is fundamentally made of information, like a giant quantum computer. Others suggest it could hint at deeper layers of reality, perhaps even supporting ideas like the holographic universe. Or maybe our universe is just a simulation. A pixel on a screen is a tiny square of light, so small that on its own it seems insignificant. It has no shape, no meaning, just a single point of color, red or blue, white or green. But put millions of them together in just the right way, and something incredible happens. Faces emerge, landscapes stretch across the horizon. The flickering grid transforms into movement, depth, and emotion. Yet none of it is real. A movie scene looks like a window into another world. But up close, it's nothing but tiny dots, shifting and blending, tricking your eyes into seeing something solid, something continuous. Change just a few pixels and the entire image shifts. The colors fade, the shapes blur, the illusion breaks. Behind every pixel is a stream of numbers, instructions that tell it when to turn on, what color to glow, how bright to shine. The picture you see in your screen right now isn't made of objects, but of information. A digital sunset is not a real sunset. It is data, processed and arranged so perfectly that it feels real. A character on a screen doesn't exist in space, but in code. Their world, built from instructions running underneath, unseen. And yet, you see it, you feel it, you believe in it. But if everything on the screen is just an illusion built from information, what does that say about the world beyond the screen? If a movie can create a universe from nothing but pixels and numbers, then what about the universe itself? What if the universe works the same way? A bit is the smallest unit of information. A simple choice between two possibilities. Yes or no, 1 or 0, something or nothing. It is the foundation of everything in computing, the language of machines, the invisible logic behind every screen, every website, every digital word. But what if bits were not just the language of computers? What if they were the fundamental building blocks of reality itself? Claude Shannon, the father of information theory, first gave us the tools to understand information as something real, something measurable. Before Shannon, information was a vague concept. Messages sent through telegraphs, voices carried over telephone wires, letters printed on a page. But he saw deeper. He saw that at its core, information was not about the medium, but about the content. It didn't matter if you sent a message by tapping on a telegraph, whispering across a room, or beaming a radio signal into space. The message itself could be broken down into bits. In his 1948 paper, A Mathematical Theory of Communication, Shannon changed everything. He introduced the concept of entropy in information, measuring how much uncertainty exists in a message. A perfectly predictable message carries no information because you already know what's coming. A completely random message, on the other hand, carries the maximum possible information because every bit is uncertain until received. With his formulas, Shannon gave us the ability to compress data, correct errors, and optimize transmission. Every modern technology, cell phones, the internet, artificial intelligence, exists because of his work. But if information is this fundamental to the digital world, why stop there? What if it is just as fundamental to the physical world? John Archibald Wheeler, one of the great physicists of the 20th century, took Claude Shannon's ideas and pushed them to the ultimate level. He proposed something radical, that at the deepest level, everything in the universe, matter, energy, space, and time, might not be made of things, but of bits. It from bit, he called it. The idea that the entire cosmos is, at its foundation, a vast information processing system. Wheeler saw a world where physical reality emerges from yes or no questions, where the universe is not built from particles and forces, but from answers to binary choices. He imagined a cosmos where every electron, every atom, every galaxy exists, not as a solid object, but as information, encoded and processed according to the rules of physics. Just as Shannon showed that all communication could be reduced to bits, Wheeler suggested that all of existence might be reducible to bits as well. At first, this might seem absurd. The chair you sit on feels solid. The air you breathe feels continuous. But look closer. Science already tells us that matter is mostly empty space. Atoms are tiny, with vast gaps between their nuclei and electrons. And deeper still, quantum mechanics reveals that particles don't even exist in a definite state until they are measured. They exist in superpositions, probabilities, wave functions of possibilities that collapse into certainty only when observed. What if this is because reality itself is built from information? Consider a computer simulation. The characters in a video game don't exist as physical objects. They are lines of code, patterns of ones and zeros interpreted by a processor. They appear on screen only when needed. Their world rendered in real time based on where the player moves and what the game's logic dictates. There is no complete world inside the computer, only data waiting to be processed. Wheeler proposed that the universe might work the same way. That reality, as we experience it, is generated by interactions, by observations, by measurements. That particles are not things that exist independently, but outcomes of binary questions. Has this electron been observed here? Yes or no? In this view, the laws of physics are not laws in the traditional sense, but the processing rules of an immense cosmic computation. This idea is not just philosophy, it aligns with what we observe in quantum mechanics. Take quantum entanglement, for example. When two particles become entangled, their states are linked no matter how far apart they are. Change the state of one, and the other changes instantly, even if they are on opposite sides of the galaxy. This seems to violate everything we know about space and time. But if reality is made of information, this makes perfect sense. Entangled particles are not separate things. They are part of the same informational structure. Changing one bit updates the entire system, just as changing a pixel in a video game updates the entire screen. This leads to an even deeper question. If the universe is built on information, what is processing it? What is running the computation? In a traditional computer, the processor determines how bits are manipulated. In physics, we might think of the laws of nature, quantum mechanics, relativity, thermodynamics, as the software that governs how information behaves. But some physicists suspect there is something even deeper beneath these laws, something more fundamental that dictates why these rules exist in the first place. One striking piece of evidence supporting the idea of the universe as information comes from the holographic principle. This theory, which emerged from the study of black holes, suggests that all the information contained within a three-dimensional volume can be encoded on its two-dimensional surface. It's as if everything inside a region of space, including you, me, and entire galaxies, can be represented as information stored on a distant cosmic boundary. This is eerily similar to the way a hologram encodes 3D images on a 2D surface. The idea comes from the work of multiple physicists, including Jacob Bekenstein. His insight into black holes shattered a fundamental assumption about the nature of information in the universe. Before his work, black holes were thought to be cosmic vaults of destruction, regions where matter and energy were swallowed, never to return. According to classical physics, once something crosses the event horizon, the point of no return, it ceases to have any meaningful effect on the universe outside. Whatever fell in was lost forever, erased from reality itself. But this posed a problem. In physics, information is sacred. The laws that govern the universe, whether Newton's equations of motion, Maxwell's equations of electromagnetism, or even Schrödinger's equation in quantum mechanics, are all time reversible. If you know the present state of a system, you can, at least in principle, reconstruct its past. The idea that black holes could destroy information outright was not just inconvenient, it was unacceptable. It meant that the fundamental predictability of physics would break down. Bekenstein saw a way around this paradox. He proposed that the information contained in an object that falls into a black hole is not destroyed, but stored at the event horizon, the black hole's outer boundary. His key insight was that a black hole's entropy, a measure of disorder and information content, should be proportional to the surface area of its event horizon, not its volume. This was revolutionary. In all other known physical systems, entropy scales with volume. But Bekenstein argued that for black holes, it was the two-dimensional surface that mattered. His formula, which later known as Bekenstein-Hawking entropy formula, told us something profound. The information content of a black hole is encoded in its surface area, not in the three-dimensional space within it. This was an early hint that reality itself might be deeply tied to information, not just matter and energy. At the time, many physicists were skeptical. The idea that a black hole had entropy, let alone a connection to information, seemed bizarre. But then Stephen Hawking's work changed everything. Hawking had been studying quantum effects near the event horizon when he made a startling discovery. Black holes are not entirely black. Instead, they emit a faint radiation, now known as Hawking radiation, due to quantum fluctuations at the horizon. The vacuum of space is not empty, but seething with virtual particle pairs that constantly pop in and out of existence. Normally, these particles annihilate each other instantly, but at the edge of a black hole, one particle can fall in while the other escapes, effectively stealing energy from the black hole and causing it to lose mass. This led to an inevitable conclusion. Black holes slowly evaporate. Over vast periods of time, they lose mass through radiation until they eventually shrink and disappear. But if a black hole vanishes, what happens to the information encoded on its event horizon? If it is truly lost, then physics itself would be incomplete, breaking the fundamental principle of unitarity in quantum mechanics, which states that information cannot be erased. This sparked what became known as the black hole information paradox. Hawking initially believed that information was genuinely lost when a black hole evaporated, leading to a crisis in physics. If true, this meant that quantum mechanics, the most successful theory in history, was flawed at a fundamental level. But Leonard Susskind, inspired by Bekenstein's ideas, argued that information must be preserved. If the information that falls into a black hole is stored on its event horizon, then as the black hole evaporates, that information must somehow be released. This led him to a radical extension of Bekenstein's work, the holographic principle. If this principle applies to the universe as a whole, it means that our three-dimensional reality might actually be a kind of projection from a deeper, two-dimensional information structure. This is another way of saying that space and time themselves might not be fundamental, but emergent properties arising from encoded information. Non-locality plays a crucial role here. If reality is made of information, and information is encoded on the structure of the universe itself, then it doesn't need to be sent from one place to another. Entangled particles don't need to communicate across space. They are simply part of the same informational entity. Their connection is not a physical link, but an expression of a deeper order where location and distance are illusions. This is why experiments testing Bell's theorem, like those performed by Alan Aspect and later by Anton Zeilinger, were so profound. They showed that entanglement is real and that no hidden local variables can explain it. The results suggest that reality doesn't behave like a system of separate independent objects, but as something more unified, something that resembles an informational network. It's as if the universe itself operates like a giant cosmic database, constantly refreshing and updating its information across space, treating distance as irrelevant, reinforcing the idea that reality is not physical but informational. So, if reality is just information, who or what is processing it? If the universe operates like a vast computational system, is there something or someone running the code? Does information arise on its own, or is it designed? If space, time, and matter are just data, where is this data stored? And if the universe is a program, then the most unsettling question: who or what is the programmer? In the early days of video games, visuals were crude and simplistic, mere blocks of color arranged in grids to resemble characters and landscapes. Pong, one of the first widely recognized games, featured nothing more than two paddles and a bouncing square, a digital echo of table tennis. It was 1972, and this was the peak of computer graphics. At the time, few could have imagined how rapidly the fidelity of digital imagery would evolve. By the late 1980s and early 1990s, pixelated sprites had taken over. Games like Super Mario Bros. And The Legend of Zelda showcased vibrant 8-bit and later 16-bit graphics, delivering worlds that, while still simplistic, felt alive. The characters had expressions, environments had depth, and players could lose themselves in adventures that were now more than just blocks and lines. Then came the transition to 3D. In 1996, Super Mario 64 revolutionized gaming with its fully realized three-dimensional environments. For the first time, players could move in a space that felt expansive, with depth and perspective that mimicked real-world movement. It was groundbreaking, but by modern standards, it was primitive. In just a few decades, technology advanced at an astonishing rate. The PlayStation 2 era introduced more detailed character models, improved lighting effects, and realistic textures. Games like Grand Theft Auto 3 and Metal Gear Solid 2 created digital cities and cinematic experiences that felt closer to reality. By the mid-2000s, the rise of high-definition gaming pushed the envelope further. The jump from the PlayStation 3 to the PlayStation 4 was staggering. Skin textures became detailed, facial expressions grew more lifelike, and open-world games expanded into vast, immersive landscapes filled with weather effects, realistic physics, and dynamic lighting. Today, we have reached a point where real-time graphics can be nearly indistinguishable from reality. Ray tracing technology simulates the way light interacts with objects, creating reflections and shadows that mimic real-world physics. The pace of this evolution is staggering. The difference between Pong and the photorealistic games of today occurred in a mere 50 years. In the grand scale of human history, this is nothing, just a blink of an eye. If graphical fidelity has advanced this much in half a century, what would happen in 1,000 years? The logical trajectory is a future where digital environments are indistinguishable from reality. Given enough time, every limitation of current technology, rendering power, computing resources, and even human perception will be overcome. The line between real and virtual will blur to the point where it ceases to exist. With the advent of neural interfaces, AI-generated worlds, and quantum computing, the simulations of the future will be more than just images on a screen. They will be fully immersive, indistinguishable from waking life. Now, step back and consider the implications. If within just a few decades we have gone from crude pixels to photorealism, then what might an advanced civilization, thousands or even millions of years ahead of us, be capable of? Would their simulations be so convincing that even the minds within them would have no way of knowing they were inside a simulation? And if this is true, what does it say about our own reality? Somewhere in the vastness of the universe, past the dying embers of ancient stars, beyond the gravity wells of black holes, there exists a civilization so advanced that their technology is indistinguishable from magic. They are not bound by the limitations of biology. Their minds do not live inside fragile organic vessels, but in structures of pure computation, vast networks of quantum intelligence that stretch across entire solar systems, interlinked, seamless, eternal. Their knowledge is unfathomable, their reach infinite. To them, time is not a river, but a vast ocean in which they can dive at will, moving backward and forward as easily as we turn the pages of a book. For them, creation is not a mystery, it is a science. They do not explore the universe in ships, they build it, construct entire realities, sculpt existence itself like a potter shapes clay, and they have built something extraordinary. A simulation so vast, so detailed, that even those within it could never detect its artificiality. In their vast computational realms, this simulation unfolds. The laws of physics are not fundamental, but programmed constraints, carefully tuned to allow for the formation of galaxies, stars, and planets. Subatomic particles are not things but bits of information, flickering in and out of existence as calculations demand. Light itself is nothing more than data moving through the system, waves of probability collapsing into certainty only when observed. Within the cold hum of their computational matrix, an entire cosmos unfolded. Not a simple model of stars and gas, but something far richer. A universe teeming with complexity, following rules that seemed from the inside consistent and unbreakable. The beings within this simulated universe would never know. They would see their world as solid, real, governed by fundamental laws of physics. They would build telescopes and peer into the cosmos, measuring light that had traveled for billions of years, unaware that every photon, every wave, every particle was nothing more than data, a perfect illusion. Inside their simulated world, galaxies spun like whirlpools of glowing dust. Stars ignited, lived and died, scattering the elements of life into the void. On one small rocky planet, circling an ordinary yellow star, a species of curious creatures arose. They called themselves humans. They built tools, cities, civilizations. They asked questions, sought meaning, unraveled the mysteries of their world, never suspecting that the very laws they uncovered were written, coded, designed. They believed in atoms, in particles, in forces that bound everything together. They searched for the fundamental building blocks of their universe, never realizing that beneath it all, there was no matter as they understood it. No substance, no fabric of space and time. There were only bits of information, ones and zeros, fluctuations in an endless field of computation. Their physicists looked into the nature of their reality and found something unexpected. An experiment with particles separated by vast distances, yet connected in ways that defied space itself. Another scientist peered into the depths of black holes and saw not destruction, but information being preserved, as if the universe itself was a vast quantum computer. Others notice something strange in the cosmic background radiation, a pattern eerily similar to digital encoding. In an icy corner of this simulated world, a quiet man gathered all the data, traced the equations back to their roots, and saw a pattern too precise to be chance. An underlying structure, as if reality itself had been programmed with an invisible syntax. Nick Bostrom is not a typical philosopher. His ideas do not dwell in the abstract corners of human thought, confined to bookshelves and quiet academic debates. Instead, his work reaches into the fundamental nature of reality itself, questioning the very existence of the world we take for granted. From young age, Bostrom displayed an early fascination with deep, theoretical problems, but his mind was never confined to just one discipline. He was, and still is, a thinker who operates at the intersection of science, technology, and philosophy, trying to decipher the nature of the universe and humanity's place in it. Bostrom is best known for his work on existential risk, the study of threats that could lead to human extinction or drastically alter the course of civilization. He has written extensively about artificial intelligence, transhumanism, and the future of humanity, warning that technological advancements, if not handled carefully, could lead to our downfall. But perhaps his most famous and controversial idea is the simulation hypothesis, the notion that our entire reality might not be real in the way we think it is, that the universe, as we perceive it, is an artificial construct, a digital reality created by an advanced civilization. This argument does not claim outright that we are living in a simulation. Instead, it presents a trilemma, a set of three possibilities, at least one of which must be true. The first possibility is that almost all civilizations at our level of technological development go extinct before they reach the capability to create detailed simulations of conscious beings. This would mean that something, war, environmental collapse, artificial intelligence, prevents intelligent species from advancing to the point of simulating entire worlds. The second possibility is that advanced civilizations do reach the point where they could create such simulations, but choose not to for ethical or philosophical reasons. Perhaps they view it as unethical to create artificial minds capable of suffering, or maybe they lose interest in running ancestor simulations, finding them irrelevant or unnecessary. But then comes the third possibility, the one that forces us to reconsider everything. If some civilizations do develop the ability to create highly detailed simulations and they decide to do so, then the number of simulated realities would vastly outnumber the number of base realities. If this is true, then the odds that we are living in the one real reality, rather than one of the countless simulated ones, become vanishingly small. Statistically, it would be far more likely that we are inside a simulation than outside of one. The implications of this argument are staggering. If we are in a simulation, then what we perceive as solid, fundamental, and real is nothing more than an intricate illusion, carefully constructed and maintained by forces beyond our comprehension. Bostrom's hypothesis does not rely on abstract metaphysics or wishful thinking. It is grounded in computing and probability. We already see primitive versions of this concept in our own technology. Video games, virtual reality, and artificial intelligence are advancing rapidly. With each passing decade, our ability to create immersive digital experiences improves. If this trend continues for centuries or millennia, It is not difficult to imagine a future where advanced civilizations could simulate entire universes, filled with conscious beings who believe they are real. But if we are in a simulation, how would we know? This question has led scientists and philosophers to search for possible clues, glitches in the matrix, inconsistencies in the laws of physics, patterns that hint at underlying computational structures. The deeper you look, the more the evidence stacks up. Like, have you ever experienced déjà vu, repeating numbers, or weird coincidences? These could be glitches, like when a video game lags or repeats patterns. It's as if reality is running on a script, and sometimes it slips. Some physicists have speculated that the universe's fundamental limitations, such as the speed of light or quantum uncertainty, could be signs of a programmed reality, constraints imposed by a cosmic computer. Quantum mechanics itself provides some eerie parallels to digital simulations. In a video game, objects do not exist in full detail until they are rendered by the computer. Similarly, in quantum physics, particles do not have definite states until they are observed. Before measurement, a particle exists in a superposition of multiple possibilities. Only when an observer interacts with it does it choose a definite state. This behavior is strangely similar to how computer graphics work, where pixels remain undefined until they are needed for display. Bostrom himself remains cautious about drawing firm conclusions. He does not claim that we are in a simulation, only that, based on logic and probability, it is a serious possibility worth considering. His work has sparked endless debate, drawing both excitement and skepticism from scientists, philosophers, and the general public. Regardless of whether we ever find definitive proof, the simulation argument forces us to reconsider what we take for granted. It challenges the assumption that reality is exactly as it appears. It raises deep questions about consciousness, existence, and the nature of the universe. If we are in a simulation, who created it? Why did they build it? What purpose does it serve? Are we alone in this digital cosmos, or are there other simulated worlds, other beings questioning their reality just as we do? And then, the unsettling thought, what if someone, somewhere, is running it? We build games, each generation more real than the last, from crude pixels to near-perfect simulation, all in a blink of cosmic time. 1,000 years more. 1,000,000. What if we're not the players, but the played? What if the code isn't ours? And what if, somewhere out there, the architects are watching?